Okay. So what I was saying that if there are this is your multiplexer, right? When there are multiple lines here, so this is your multiplexer, and decoder will be there is one line here and an output. Assume that there are multiple lines, so it will select that this input will go through which line. So if you go with multiplexer here, then what will happen that there will be multiple lines in one line address of there will be multiple lines here, right? Like this, and you want to pass one line. But here, if you understand the DRAM design, then there is only one address bus. Like so this address bus, there will address will come first, row address will come, and then after some time a column address will come through this line. So once this column address will come, there a decoder is required here to decode that okay, this column address is for which column. So that's why there is a decoder used here. Okay, so before starting today's lecture, I have two, three small announcement. First two announcement are related with your mid-sem feedback. So in mid-sem feedback, I have got two comments. So these two comments, I feel these are important. That's why I'm discussing here. The first comment was that the concept that discussed in class and the questions that asked in mid-sem or in quiz are not matching. The questions are more tougher. So I agree with this point that yes, the questions that I have given a little bit on tougher side than as compared to what I discussed in class. But there is a purpose for it. Purpose for it is you can see there are hundred at least there are 100 students in this course. So when I teach something in this course, at that time my motive is that I should go with everyone. Means if someone is a little bit slow in understanding, no one is weak. I don't consider anyone is weak. Some people some students need some longer time to understand a concept, and that is the difference. So that's why when I teach, I like to go with everyone. That's why I teach. I don't go with very high-fi concepts. Sometimes I most of the time when I explain with the basic concept. I explain from the basic level. And if I want to explain something very advanced level, then what I do, I just give some assignment, right? If some of you already know all this thing, then for them sometime I upload some extra lectures. So but when we go for exam, then I cannot follow this procedure, right? Because exam is a place where I have to decide that which is number one and which is number 100. So I have to follow some strict policy. So when I teach in class, then my main motive is to teach something to you, to explain something to you. But we have to follow some procedure called exam, which is there in our academic system, right? From many years. If someday someone decided that there should not be any exam, then I think I will be happy, because I believe in teaching or explaining something to students. But anyway, we have to follow this, because this mark CGPA is depend on for many things, right? Career opportunities and all, right? So in that case, that should be a standard based on which I have to measure that who is number one, who is number 100. That's why sometimes the questions should be, every question cannot be easy, right? Some questions should be there which based on the concept, or some questions should be there who can be only answerable to those students who have given more time to this subject, and they understood the concept more better in a better way. That's why questions are given in a little complicated, in complex way, and not directly the way we teach in a course. And we have to do this. There is no other way. And the second comment was that not to disclose marks publicly. So I think at the beginning of this course, I've explained it that it is not possible that I'll share the marks publicly. Means all of you will know the marks, because it sometimes it is required for you also to understand that what is the average mark going on in the syllabus, that what are the performance of other students. So uh, uh, and also the information that I'm sharing is it's not a private information, right? If someone put an RTI to us, then and that time also I have to share this marks. So it's not like that a private information sharing with all. So that's why most of the faculties do the follow the same process, that we don't share the answer script and all, but we share the marks. Okay. And there is a one more point to discuss here is regarding the hybrid classes. So I have received some mail. I think you can also observe there is a discussion on Google Classroom about the hybrid classes. See, I don't have any personal problem with hybrid classes or offline classes. Basically, we want that they have offline class should start, because online classes somehow it's not much interesting. But the problem is with hybrid classes is that some faculties are taking hybrid classes because they have taught the same subject in last semester also. They have the recording of last year, so they can share. But for me this is not the case, and if I go and take offline classes and at the same time I have to record the lectures again, then it is difficult. So now the next point is, there are two three options. One option is I just share the slides and all for those who are not in campus. That is not a justice for them. So the only option left is to record or live stream the lecture that I will take in offline. But for that I need equipments, and I need help from department. So that's why I'm planning. So this I don't know how much support we'll get from institute or department regarding that, regarding the recording or live streaming our lectures. But still I'm thinking one point, because since I have a tab and in the tab I can write. So what I'll do, next week or this weekend I'll go to the lecture hall and try to connect my tab with the projector machine. And if this is successful, then what I can do, that I'll not use blackboard or I'll not use whiteboard of the classroom. I'll use the same whiteboard of my tab in offline classes also, and I'll try to take the lectures offline. So what will happen in that case, if I simply record the way I'm recording the lecture, then all and the entire lecture can be recorded. And I'll use a Bluetooth headphone for talking from long distance. So I think I'll try this setup and this weekend, and if this setup is successful, then I'll go with this. I'll go with this setup. There is a question, I think, no? Yes.
Yes, sir. Regarding this hybrid classes,
Uh,
sir, thanks a lot for the update. Sir, with the help of academic secretary, actually, we have mailed to
huh,
Dean of Academics
huh,
regarding facilities for recording offline classes.
huh.
So, yes, sir, if there's any reply regarding that, I think we'll inform you.
Yeah, so I'll also try from my side in this weekend that if the setup that I'm saying, right, that I'll try to put my project, my tab in the projector, and I'll try to write on the whiteboard. The only thing is, right, at this moment I'm taking this class and sitting in my chair, right? So and in class, if I need to stand and at the same time I need to write, I'll check all these possibilities, that is it possible or not. If this is possible, then I'll start offline, if even if there are no support from the institute side. Okay, so with all this information, let us start today's lecture. So okay, just 1 minute. Yeah, so from last class we were discussing about cache memories, and last class I've explained the concept of blocks, word, and this and some other concepts. So these concepts are very important. I hope you revise this concept. I explained that when a core request for a data, then core request for a word. But when we fetch data from main memory to cache, we fetch a data in terms of block. So a block has multiple contains multiple words, right? And every word or block, it is a byte addressable. So all this concept I've explained in last class, I'm not repeating here. So you should understand this concept. And then I have explained you the concept of direct map cache. In direct map cache, this is a cache where there are multiple rows. The rows are called set here, and there is only one column. And in each location here, this is called entry. So in each entry we can store one block. There will be block one, block two will be in this position, block three here, like this. Okay, so the number of blocks you can place in a cache, in a direct map cache, and the number of set in a direct map cache are same. If the number of blocks you can number of set is n in a direct map cache, then the number of block you can place in n is also in the cache is also n. So this is the property of direct map cache. And I have also explained you that if since the computer is byte addressable, then every byte has a address. So whenever the core will request for a word, that word will have a address. So if we assume that this is a 64-bit address, then out of this 64 there will be some bit here, these are called offset bit, block offset bit. Okay, that I have explained in last class. Okay, after this there will be some bit here is called index bit, or you can say set index bit. So based on this bit we first decide that okay, in which set this block will be mapped. Suppose this index bit are 0011, so it is saying that 0 1 2 3, in set number 3 this block is will map. So this is the only location for this block to place in the cache. So if this suppose this block is b5 and currently in this position b4 is placed, now to place b5 we have to replace b4. There is no other alternative. Even if you say that these three locations are empty, we cannot place it there because of the mapping policy. We have to replace b4, and in the place of b4 only we have to place b5. So all this point I have explained, and the remaining bits here we call as tag. And these tag parts are also stored with the cache. So actually the cache actually look like this, that I also have explained in last class, that with the block we also store the tag part will be stored here, like t1 t2 t3 t4 tag will be also stored. So every time when there is a request come for, suppose now after b5 the core is requesting for b2 again. So and again the address of b2 will be divided into offset, index, and so index will be here 010, sorry 001. Okay, so it is saying that okay, it is going to set number mapping in set number 1. So no problem. Now we have to ensure that the in set number 2 the block b2 is present, not any other block. So for that the tag, this tag and this tag, these two tag will be compared. If these two tag are matched, then it's saying that it's the same block. So in that case we will say cache hit. And if these two tags are not matching, then it will say tag miss. So all this thing I've explained in last class. If I go with this diagram, then if you remember this diagram I've explained in last class, that see this is your 32-bit address, and from this address this part is your byte offset, and then after byte offset there are 10 bits here for set index. Why 10 bits? Because in this cache they have used, there are 1024 sets are there. See, since 1024 sets are there, so you need 10 bits to uniquely identify a particular set. So so based on this here, suppose they are considering this, if this set is this, based on this index, if this is the place, this is the set where the block will map, then what they are doing, see, the tag of the incoming tag of this requested address and the tag that is present here, they are comparing here. And if this compare is true, then it is a hit, otherwise it's a miss. And at the same time the data is available here, so the data will be taken and not will be decided by the decision of hit and miss. If the decision is hit, then this data will be forwarded to the upper level or to the processor. And if this is not a hit, then this data will not be taken, because in this case we have to go to main memory and fetch the data. Okay, so this all this concept I have explained in last lecture. Today I'll explain you one more point. Here you can see that the entire data is going to the processor, right? But that is not the case, because the entire data is actually the entire cache blocks, right? And as I said, core request for a word, it's not request for the entire block. So it means that these part, the data part needs some more modifications. So a better design will be like this is a better design. So here also it is the same direct map cache, and you can see the data part is extended here, just the data part. I don't know, my not sure if now it is showing. I think now it is showing better. So because see, this is the data path, this entire thing is data path, and this data part is divided into multiple words, suppose. So first same as based on tag index, it will select a particular set, and in from the same set it will come, the tag will be compared here. So based on this it will be decided either hit or miss. But at the same time you can see the entire data is going to a mask. And previous picture there was only one line, but here there are one line for each watt. See, you can say there are multiple watts, and which watt to be taken to be considered is based on the offset part of this address. See, because we never use the offset part, and now you can see the offset part will be required here. So the offset part will be used, the block offset or the offset part will be used, and based on this instead of sending the entire data, which is the entire block, we'll send a particular word from this block to the processor. Okay, so this point you have to understand. I'll never explain it again. Most of the time what we will do, we'll go with the simplified diagram. Simplified diagram means most of the time we'll explain in this way, but actually this is not the correct diagram. Correct diagram is the data is actually divided into multiple words, and we will use the offset and use another multiplexer to decide which word should go. So the actual design is this, but we will rarely use the design. Most of the time we'll go with simplified design. So you have to understand all these concepts here. So now let us go back to the book. So I last class I stopped here, so I'll again start from this part. So this part here, the question is the block size. So normally, if the block size is 64 byte or 128 byte or 256 byte, or we go with a smaller size block like 32 byte block size, which one is better? This is the question now. So suppose, just 1 minute. So suppose you have a set you have a direct map cache where there are multiple sets here. So assume that there are 1024 set, and the block size is 64 byte. Okay, so block size 64 byte means each block here, suppose b1 b2, these are your blocks. So these are actually each of b1 of size 64 byte, b2 of size 64 byte. So the size of this cache will be 64 kb, right? Size of this will be 64 kb, because each set here is of 64 byte, and there are 1024 byte sets are there. So total size will be 1024 into 64 byte, which is 64 kb. Okay, so now if I increase the byte size from 64 to 128, suppose from 64 to 128, double. So if we double the bytes block size, but we keep the cache size same, means the cache size is 64 kb, so cache size remains 64 kb now, but my block size is 128 byte. Then what will happen? Number of sets will reduce, right? Number of sets will reduce from 1024 to 512, because now this much space is required to store one block, because block sizes increases. So the this point here is, if you increase the block size, then your number of set will reduce, and the number of possible location where you can place a block will be reduced. Previously there were 1024 blocks you can place, right? Now if you increase the block size, then you can place only 512 blocks in the cache. And if you decrease the block size, then it will do the opposite thing, right? For example, instead of 64 byte, if you go with 32 byte block, then number of set will increase from 1024 to 2048. Just 1 minute. हेलो श्वेता जी, मेरा क्लास चल रहा है, मैं क्लास के बाद फोन करूं? Okay, there are some question. When a block is moved from main memory to cache, is the block removed from the main memory or stays in main memory? And what about when it is from L2 cache, L1 cache? Okay, Aditya, at this moment, let us consider there is no L1, L2 cache, just one level of cache. I think in next lecture, I'll introduce multi-level caches. So I'm not answering your last question, but to answer your first question, when we move a block from main memory to cache, so we do not remove it from main memory. But the question is, if you are sending a read request, if you only want to read the content of main memory, then it is everything is fine, right? But when you want to write something, then the block they will fetch in the cache, and if you update something in the cache, then the updation is in the cache only, right? So this point also I'll discuss. So Aditya, what you can do, you please wait till the end of today's lecture. I hope by end of today's lecture your first question will be answered, and your second question will be answered by the next lecture. Okay. So what I was explaining here is the block size. If you increase the block size, then the number of block possible to place in a cache will reduce, and if you decrease the block size, then it's do the opposite thing. And now the question is, what should we do? Should we increase the block size, or should we decrease the block size? What should be the ideal block size? So here, if you see in this figure, in x-axis here you can see there are different block sizes are taken: 16 byte, 32 byte, 64 byte, 128 byte. And in y-axis you can see the number of misses. So you can see the number of misses are decreasing with the 32 and 64. If the block size is 32 and 64, initially if it is 16, then also it is saying high number of misses. But if the block size is 32 or 64, it is showing less number of misses. And again, if you increase the block size, again the misses are increasing. So it means that you cannot go with a much smaller block size, you cannot go with much higher block size. So the standard size is 32 or 64. Most of the time we go with 64 byte block size. Now the question is, if we keep on increasing the block size, why it is not giving better performance? What is the advantage of blocks? Why we are not going with block size 1 watt per block, right? Why we are going 4 watt per block, 5 watt, 8 watt per block? What is the advantage here is spatial locality, right? I have already explained you that if core is requesting for a particular watt now, then in near future it will request for the nearby watts. That's why we are moving a block at a time from main memory to cache, assuming that the nearby blocks will be considered in near future. But if you go with a much bigger block, then maybe these all the nearby watts will not be because suppose this is the watt that is now cache is requesting, and maybe these are the nearby blocks which will be accessed by the core. But if unnecessarily if you fetch this much huge block and this part will never requested by the cache, then this is a wastage, right? You are not using this much spatial locality. So spatial locality will also give you a benefit up to certain extent, right? That's why this is the one problem. Another problem is if you increase the number of block size, then as I have said that then you can only place less number of block in the cache. So the conflict misses will arise much faster. Conflict means, as I said, if there is a block present here, suppose block is called b5, and core is requesting for another block which is also mapping in the same position, then you have to remove b5 to place the new. That is called conflict. So if the number of position placed previously, suppose it was 1024, now if you reduce it to 512, then then these type of conflict will increase. So that's why if you see in the graph that even if you increase the number of block size constantly, then also it is decreasing the performance. Why? Because of this problem. And even if it is the block size the is too low, then it cannot use all the advantage of spatial locality. So that's why it should be either 64 or 32 most of the time. So now maybe one question coming, how you have designed this graph. So that's why I'll take 5 minutes here and I'll discuss something which is not directly related to today's lecture. So now I'll discuss how to design this type of graphs. Okay, you must. I think this point is clear that since y-axis is miss rate, so the more number of misses is the worst performance, right? If there are two computer here, C1 and C2, so which one I'll suppose here the miss is 500 and here the miss is 100, then this is a better computer, right? Less miss means more hit in the cache. More hit in the cache means it is taking less time to execute, because miss means we have to go to main memory and the time will be more. So I hope you understand this type of parameter, that miss, in terms of miss, less is better. If we go with instruction part cycle, more is better. So do remember all this point. Now for this type of analysis that this graph is showing, normally we cannot go with real machine, right? For example, if this is the laptop, obviously in this laptop there is a processor, there are some cache memories exist, but I cannot change the block size of this processor because it is fixed, right? So how can we run different application on different block size and collect data as this graph is showing, right? For this we use simulators. We have some simulator, and on this simulator we can do anything. We can change block size, you can change the cache size, everything we can change, and then we can run some application, and based on this we can collect the results of number of meals, number of hits and all. So those simulators are very important to work in computer architecture community. Otherwise it's not at all possible to go with different combination of processors to run and to do small experiments. So what we will do in this course, that since there is a project work you have to do, so in this project work we will understand a simulation tool. Based on this simulation tool, you will be also able to recreate the result that they are showing here. So there will be by the end of this week, your assignment will be clear to you that what I'm expecting from your side. And I think in next week at the beginning, I'll share the recorded video. So I have to record that video because, and I'll share it. On that video, I'll explain you some basics of simulations and all, how to start simulation. See, there is a term here written spec CPU 2000. So what are these terms and all? For all these thing, I'll share a recorded video and I'll share. But yes, by end of this week, you'll understand that what I'm expecting from your side in the project. So basically, you have to work in a simulation tool, and that simulation tool is written in C++. Okay, so now coming back to today's lecture, I think the advantage of bigger block size and smaller block size I have explained. Now handling cache misses. So to explain this again, I'll go here. Let me remove all this thing. So uh, we know there are two types of instruction, we know, right? Load and store instruction. So other instructions are also in, suppose there is a add instruction here. So if we know the pipeline stages, first stage is fetch, right? So in the fetch stage, we go to memory and fetch the instruction. I think I have sorry, I don't have this. Just 1 minute. Data path. Yes, this is the data path. Okay, so if you remember, this data path I have used pre-meetsem. So here, this is the instruction memory I saying. So we have to fetch from instruction memory. This is actually the cache memory. This is called L1 cache. So okay, so since at this moment I'm not dividing cache into my L1 L2, so this is actually instruction cache. Cache is divided into two parts: instruction cache and data cache. So here, this is interacting with instruction cache. And load and store instruction also interact with data cache. That is called data. There are two cache memories. Okay, so here every time, suppose what I was explaining here is miss, right? So just 1 minute. So when core request for a word, then core request for a word. So I'll not discuss word here. So make it simple. Assume that core request for a block. So when core request for a block, we'll search the block in the cache. How we search? We compare the tag, right? And if we compare if the tag are matched, then it's a hit. You know what we do if there is a hit. But if there is a miss, then what we do? We send the request to main memory, and from main memory we fetch the block and store it in the cache, and then we send it to the core, right? And when we fetch the block from main memory and store it in the cache, you have to understand that when we place the block in the cache, we have to strictly follow the mapping policy. If the according to mapping policy, the block is mapping to set 0, then we have to map it in set 0. There is no other alternative way. Okay, so this is so for load instruction, whatever request we do, it's for reading some data, right? Load means reading something from memory, and store means writing something from memory. So there are two types of memory requests possible: read and write. Let us just concentrate on read first. So if it is a read, then if it is for read request from core, then if there is a miss, then we'll go to main memory, fetch the block, and store it here. Suppose the block is called b1. Okay, reading something. So when we read something from main memory, we don't delete it from main memory. Just we'll take read it, and we'll reading means we'll make a copy of it and store it in the cache. And no problem here, because it is reading. So the data, the value that is stored in main memory of b1, and that is the value that is stored in the cache of b1 are same thing. It is just reading. But what about in store instruction? Store instruction means we want to write something in this block. So suppose after some time the core is requesting for another block. Suppose in B3 the core wants to write something, and assume that B3 is mapping in this set. But at present the block is not there in this set. So if the block is not there in this set, then we have to fetch the block from main memory here. So this fetching part is common for both reading and writing. So read part I've already explained that if there is a read request and block is not in cache, you have to fetch the block from main memory. This same concept is true for write also. If you want to write something on a block and the block is not present in cache, then you have to suppose block B3 is here in main memory. So you have to fetch the block from main memory to the cache, and you have to store the block here first, b3, and then you will write in b3. So maybe one question someone can ask, that what is the advantage of doing this? If core wants to write something in b3, directly go to memory and write it. What is the point to bringing it back? we are bringing B3 in cache and then writing because of principle of locality. Be it a read request or a write request. When I explained principle of locality, I said if core is accessing का मतलब read write दोनों होता है. So if a core is accessing a block, then principle of locality will apply on it. So because of principle of locality, we first fetch the block B3 in the cache and then we'll write on it. So suppose store instruction is executing, so we'll first fetch the block in B3 and we'll write something on B3. The moment you write something on B3, this B3 and this B3, they are not same. So the B3 in main memory is storing the old content and B3 in the cache memory is storing the new content, right? So but this is not a problem because every time the core will request for the block, first will search in the cache, and from cache you will get the updated version, no problem. Only problem arises when your computer will power off, right? So what will happen at that time? So or if this block B3 is removed from the cache, then what will happen at that time? So that's why to handle these questions, there are two techniques to handle writes. I hope you are understanding that what is the difference between read and write. The moment you write something in the cache of B3, then there will be two different copies of B3, right? The copy that is exists in main memory, it is storing different value, and the copy that is stored in cache is storing different value. So how to handle this? So these are explained in this section, handling cache misses. So there are two techniques basically. I'm not explaining all this concept. You read it by yourself, you'll understand. There are two techniques that I'll discuss. One is called write throw. In write throw policy, if I again go back to my example, maybe I can show it in parallel in two sides. Yeah. So in write throw case, what happened if the block, suppose after fetching the B3 here, if the core want to write something in this B3, then this updation will be simultaneously done in this B3 as well as the main memory in both places. So every time core wants to update something in B3, then the same updation will be done in the both places. Okay, but there is a disadvantage because we know that B3, suppose if I expand B3, suppose this is your B3, there will be multiple words, right? And maybe first time core wants to write something in this word, so only this word is updated. After something, maybe core wants to update in the same block B3, but the word that it wants to change is this. So in that sense, every time if we go with the write throw policy, every time the core wants to change a particular word, the same updated value we have to do in the main memory also. So the advantage here is both main memory and cache will be in same path. If there is a value changed by any code, then that change will be visible in both main memory and cache. But that is unnecessary, right? Because if we want to do this, then every time that you have to send a request from the processor to memory, you have to understand that cache and main memory are not in same chip, right? Main memory is placed in off chip, that I've explained at the beginning. So unnecessary, you have to send lot of communication, you have to do a lot of communication between main memory, and it will make your program very very slow. So another option is we will not write immediately, we'll just mark that okay, the value that is stored in B3 is updated. For that we use another bit called dirty bit. Last class I have explained that you need one valid bit, right? Tag and then a valid bit. Now I'm introducing one more bit called dirty bit. The moment you fetch a block in cache and you updated something in that block, at that time we'll mark it as dirty. So and then within a short period of time, if the core will request for multiple writes in this block, then all writes will be done in cache only. There will be no communication with main memory. Obviously main memory is storing the stale copy, no problem. Why no problem? Because whatever request will there, no one will directly go to memory, right? Everyone will first come to cache. So and cache has the updated copy, so no problem. So when the write will be if we don't follow the write throw policy, then what is the alternative policy? Alternative policy is called a write back policy. In write back policy, what we do, oh, after all these writes, this block will be here, and as I said, after some time, suppose core is requesting for a block called B10, and this block B10 is also mapping to the same set here, in the same set. In that case, what will happen? If B10 is also mapping to the same set where B3 is stored, located at this moment, then we have to replace B3, right? And in place of B3, we have to store B10. So when we'll replace B3, we'll check whether the block is dirty or not. If the block is dirty, then the copy that is currently in the B3 will be written here in main memory. and then only the B3 will be removed from the cache. So in this way, we are maintaining the consistency between main memory and cache. So I hope you are understanding the write throw policy, difference between write throw and write back. So there is an intermediate solution also, that you can use write throw policy, but you can reduce the overhead of write throw using a buffer here. So this is called write buffer. There will be a write buffer here. So again, I'm going back to write throw. I hope I have explained you write back. In write throw, as I said, every time there is a write in B3, you have to write it in main memory. Instead of doing this, what you can do, every time if you want to write something, you just just write it in the write buffer, that I need to write B3 in main memory. And once you have written it in write buffer, you assume that the write operation is done and you can continue with your process. And now it is the responsibility of write buffer that slowly write it back to main memory and get the acknowledgement and remove it from here. Okay, so this normally do by the write buffer. But again, the buffer size is limited, right? So if the buffer size is limited and the buffer becomes full again, then there will be no option that you have to wait for it. So a write throw policy, even if you using write buffer, then also it is not a good option. But normally what we do, even when we'll go with write back policy, then also we use write buffer. What is the advantage here? So as I said, in write back policy, when we remove B3, we'll remove B3 only, we'll write back B3 only when another block, suppose B10, wants to place in this position. So at this position, when we want to remove B3, we have to, and the block B3 is dirty, we have to write it back to main memory. But without waiting for, because at this moment also writing back to main memory is time consuming, right? We'll send the block to main memory, and after writing it back to main memory has to send an acknowledgement that, okay, I have written it successfully. Then only you can remove it from cache. Instead of doing all these things, what you can do, simply remove move B3 from this cache to the write buffer and remove B3 from cache, and then allow B10 to store here. Okay, and then the remaining writing process of B3 will be continued from write buffer and main memory. So write buffer is used for both write back as well as write throw policy. So all these things are discussed in this section. First they have explained write throw, then they have explained write buffer, then they have explained write back. So I hope I have explained these concepts. And then after this, they have shown a real example of cache memory here. If you scroll down, this is the real example of cache memory, but I think I have already explained you this diagram, right? In this diagram, they explain that, okay, when every time we are saying about block, but actually it is not block, right? Code request for a what. So after tag match, what happened with that, how to find out the what. So that's why we are using a multiplexer here. But I think this diagram I have already explained, so I'm skipping it. But you have to read this section by yourself. Okay, and at this moment you can ignore the concept of split cache. If it is required, I'll explain it later, but at this moment you can ignore the concept of split cache. Okay, then the next section is measuring and improving the cache performance. How to measure the cache performance? So if you remember, pre-midsem, we measure the performance of a computer, like there are two computers, C1 and C2, and if we run a particular application called A in both the computer, and then how we can say that which computer is giving better performance? The computer that take less execution time. Suppose here it is taking 10 nanosecond and here it is taking suppose 20 nanosecond. Then C2 is the C1 has the better performance, right? So if I remember, most of the time we only discuss about the CPU execution time, right? So CPU execution time means, if I go back to the data path, so if you remember, every time when we explain this data path, when we are discussing about pipelining and all, we just said that fetch stage and mem stage. In fetch stage, we assume that it will go to memory and fetch the data. In mem stage, we say it will go to memory and either read the data or write the data there. Okay, so what assumption we have made? We have made a big assumption there that every time there is a hit in the memory, right? Even if and here I am saying that this is a cache memory, right? Either instruction cache or data cache. So when we explain whatever explanation we have done in before midsem, there we assume that every time there is a hit in the cache. What about when if you go to write something in mem stage and there is a miss in the data is not there in the cache? If the data is not there in the cache, then it will be miss, and you have to go to main memory, you have to fetch it. So there are some stall required there. So those stall I have not included before midsem. So the pipelining that we have shown is the ideal pipelining, right? There will be some more stall there which cannot be solved by forwarding also. So in what happened in normal in modern computers, the instruction that we execute, normally they don't execute in this way. Normally there are two things. First, out of order execution concept is there. This is one option. Another option is, instead of fetching one instruction at a time, actually modern processor can fetch multiple instruction at a time. So all this advanced level concept I will explain later. Those concepts are not required now. So only here you have to understand that if you want to measure the exact cpu time to run a application, suppose this is an application you want to run in this computer c1, then you have to consider two time. First is cpu execution clock cycle, that how much time it took in cpu to execute, and memory stall clock cycle means how much time it took to fetch data from memory. Okay, so suppose the computer requested for a word, and a word is not in cache. Okay, so at that time we assume that and to fetch the data from main memory, it take 100 cycles, suppose 100 nanoseconds, suppose. So these 100 millisecond or nanosecond, this 100 millisecond is actually memory stall cycle. So here you have to separate these two terms, that cpu clock cycle, the exact number of cycles required in cpu to execute a task, and number of cycle it is required in the memory means number of cycles is stalled in the memory. Okay, and then this, both this will give you the total cycle, and if you multiply total cycle with clock cycle time, then only you will get the cpu time. So I think from these two parameters, cpu execution clock cycle, the first parameter is known to you, because before midsem we have discussed this parameter. So now let us discuss this parameter, memory clock stall clock cycle. So memory stall clock cycle, as I said, in memory stall there are two things: read cycle, read stall, or write stall. Either will go for read or write. So if you only concentrate on read stall, then how can you calculate read stall cycle? First, you calculate the number of reads in your program. Or here I've said application, right? This is application. So they are saying, instead of application, they are saying program. So first you find out that how much, what are the number of reads in your program or in your application. So this is the number of reads in your program, and read miss rate. Read miss rate, or you can say miss rate means miss per memory access. So here read miss rate. So here the first two terms, that this multiplied by this, so this term is actually saying the total read miss, total read miss. Okay, multiplied by read miss penalty. Read miss penalty means the cycles required to fetch data from main memory to the cache. This is called read miss penalty. So total read stall cycle will be total read miss multiplied by the penalty of one read miss. Okay, so the same thing for write miss also. If you consider a write miss, this two term, if you multiply it, then this is giving you total misses, total write misses. Okay, total write misses. How? Because number of write per program is giving by this, and you have to remember miss rate means miss per memory access. So write miss means write miss per memory access. Okay, so multiplying these two is giving total write miss in this program, and then write miss penalty. Okay, this part is fine, but what about the last thing, plus write buffer stall? This is not required in read, because I have already explained, when you go for read, we no need to use write buffer. But in case of write, we have to use a write buffer. So if that write buffer is not full, then no problem. But if that write buffer is full, then in that case we have to wait, right? We have to wait. We cannot perform any write, because the write buffer is full. So that is called write buffer stall. If the write buffer is full, then it's called write buffer stall. But if we concentrate on write back cache only, then it is a rare situation that the write buffer will be full. So you can ignore this part. When you will calculate write cycle, you can ignore this part. And if you ignore this part, then you can see that this part and this part are almost same, right? So hence, if you scroll down here, that say the same thing, and instead of separating it to read cycle and write cycle, they will say this memory access per program. So it is considering both. Memory access means read and write both, and miss rate. So it's not read and write. So this part is total memory access by this program or application. Okay, and then multiplied by miss penalty. So most of the time memory stall cycle will use this formula, will not separate it in terms of read and write, because it is only important to separate read and write when the write buffer queue will be full. But as I said, if you go with write back policy, then it is a rare case, and they have also mentioned the same thing here. That's why this will be our final formula for memory stall cycle. I hope you will understand it. You read it once again, because after this formula, you can see there are some numerical problems mentioned. I'll not discuss this numerical problem here because I don't have time. But I'll advise you to follow this numerical formula, because in exam I may ask you the numerical questions also. Because I'm explaining the basic concept, I'm explaining the formulas, and it is your responsibility to understand some numerical problems related to these formulas. Okay, so I think CPU time combining with memory I have explained, but one important, more important point here is, if we go to the data path, and in data path we assume that if fetch means we'll go to memory, and now we have separated the CPU time and memory stall, right? So in CPU time, the heat time, so memory stall means there is a miss in the cache. If there is a miss in the cache, then we'll go to main memory. So that part we call memory stall. But what about heat? If there is a heat in the cache, then that, obviously, even in case of heat also, you need some time to access the block from cache, right? So that is called heat time. So that heat time is normally included in CPU execution time, right? CPU stall time and memory stall time. So in CPU time and memory stall time, right? So in CPU time, we normally consider the heat time. Okay, but now if your cache memory is not small, if you increase the size of the cache memory, then obviously your heat time will also increase. So if I go again here, and if I say that, okay, previously my cache was of this size, 32 KB. Okay, so in that time, the access time was suppose 5 nanosecond. Now if I increase the cache size from 32 KB to 128 KB, and then the access size may also increase from 5 nanosecond to suppose 20 nanosecond. So hit time is increasing here. So if you increase the hit time, so if you remember, suppose in mem stage, every stage in pipelining take one cycle, right? So in this case, it may be possible that you need to increase the cycle time. Previously, suppose this is your cycle time, now one cycle you may extend the cycle time, or you may go with multi-cycle mem stage, right? So it means that hit time is also important. You cannot assume that hit means, if you just include CPU hit time in CPU, is not the correct thing. So if you want to measure the exact execution time, then you have to consider the hit time also, because many time, in many situation, hit time is more than one cycle. So a better term here is called average memory access time. Average memory access time means, suppose you have a cache memory here, and you are going for multiple requests here, r1, r2 to r10. So out of these 10 requests, maybe 7 are hits and 3 are miss. So average memory access time means, for the 7 into hit time. Okay, 7 into hit time plus 3 into miss penalty. Okay, so this is actually called average memory access time, or AMAT. So this is the formula of AMAT: total time for a hit plus miss rate into miss penalty. This is called average memory access time. And this average memory access time, or AMAT, is a very good parameter to measure the performance of two memory or memory system. Suppose you have two cache memory, C1 and C2, then how to measure the performance of these two cache memory? Then this is a very good parameter, average memory access time. So we have to remember this formula also, what is called average memory access time. So there are some formulas I've already discussed in class, that is, for example, instruction count, CPI, IPC, right, miss rate, and now I'm saying average memory access time, AMAT. These formulas are these terms are also important, these formulas are also important. Don't just memorize this formula, you have to understand it. Means high AMAT is good or low AMAT is good. Suppose there are two computer, one computer has there are two cache memory. Suppose one has AMAT 10, another has AMAT 20. Which one is better? So high IPC is better or low IPC is better? All this thing you must understand. Don't just memorize the formula. Memorizing formula will not give you any advantage. You have to understand the concept, and then only you memorize the formula. First you have to understand. Okay, then reducing the cache misses by more flexible placement of block. So from here I'll explain you another point here is called reducing the cache misses. So if we go back to the cache memory again, I think I have removed everything, right? So this was our cache, right? Till now so far we have only discussed direct map cache. So this is our direct map cache. I have assumed that 1024 sets are here in this side, and each set can store only one block, right? So now here the disadvantage of this type of direct map cache is for each block there is only one position, right? Suppose there a b5 block is stored here. Now if core request for another block and which is mapping in this location, then you have to remove b5. So conflict misses is more in direct map cache because there is only one location for b5. That is, it's not possible that you can store b5 in two different locations, right? So that's why this is the disadvantage of direct map cache. So to handle this, there are two more options available. One is called set associative cache and one is called fully associative cache. In set associative cache, what you can do that in every set you can store more blocks. Let me just expand it like this. Sorry. It can be like this. So in every set, suppose instead of storing one block, now you can store three or four, suppose four block. This is your set associative cache. Okay, so now at this point what is happening, so set concept is remain same, but here you can say there are multiple columns are there, so these are called ways. Set is fixed, so row are called set. Now there are four ways in each set, right? So now if the core is requesting for another block that is b10 and it is also mapping in this set, then you no need to replace b5 because there are three more positions, so you can store b10 here, right? So it means that in case of set associative cache, there are multiple positions available for to store a block. So here, if you want to place a block in the cache, first you have to decide the set. Suppose this is the set where you need to map. Once you decide the set, then inside the set you can see there are four ways. There are four positions. Out of this four position, the block can be placed in any position. So now maybe the next block is placed here and next block is placed. Suppose B15 is placed here. Okay. Now after this, if the code is request for another block like b25 and it is also mapping in in the same set, then now the set is full. And if you want to place b25 here, then you have to remove one block, because previously it was very easy in direct map cache. There was only one block b5. If you want to store b10, remove b5, place b10. Now here you want to place b25, there are four options. Out of these four options, which one you want to remove? That is called, you need a policy here, right? And that policy is called replacement policy. So all these things I'll discuss in next class, or since there are no time today, I'll stop here. In last class I'll start from the set associative cache again. First I'll explain set associative cache, then I'll explain fully associative cache, and then I'll explain you the concept of replacement policies. Okay, so I'm stopping here. If you have any question you can ask. I think Aditya, you got your answer, right?